Hello everyone, I have encountered issue with my visa application. Therefore, I'm unable to attend the presentation in person. So I pre-record this video. And here we go. I'm going to talk about Apple UserFS, which means running file system code in Userspace. I will give an overview of the implementation of UserFS and share some vulnerabilities that I have discovered in it. I am Pantin F, a security researcher from Ant Security Lightyear Lab. I mainly focus on iOS and macOS security. I attended Black Hat in 2021 as a speaker. I'm glad I could attend Black Hat again. In my previous talk, I shared a file system vulnerability. It is a local privilege escape bug. Since iOS and macOS share code base, I assumed that this bug should work on iOS too, but I was wrong. The same POC doesn't crash iOS. I noticed that iOS handled file system in a different manner, introducing a new mechanism called UserFS. It is possible that UserFS prevents this vulnerability, but I can't be certain. At the time, I was unsure whether this bug affected iOS or not, so I added it to my to-do list. However, as we all know, to-do means never do. But this time, things are a little different. 2 years later, I'm still curious about why this bug didn't work on iOS. I finally make up my mind to figure this out. I spent some time studying UserFS extensively. It turns out that this bug does indeed affect iOS as well, in a different way. Alright, let's get started on today's topic, UserFS. Firstly, what exactly is UserFS? Apple introduced a file manager app called Files in iOS 11, which allows users to access files stored on external USB flash drives. According to the iPhone user guide, it supports various file system formats, including the commonly used FAT32 file system. But when analyzing iOS kernel cache, I found that only APFS and HFS support were present. There is no MS-DOS kernel extension in kernel, which is the backend of FAT and EXFAT file system. Instead, Apple implements the FAT file system as a plugin in the form of a DLI running in Userspace. You can find all supported file system plugins under UserFS framework, but the plugins are not the sole components of UserFS. This image provides a comprehensive overview of UserFS, including LIFS kernel extension, a set of daemons, XPC services, framework, and file system plugins. Most of them run in Userspace. UserFS is designed to work with external storage devices. So let's begin by connecting an external hard drive to an iPhone like this. On iOS, LaunchD registers a launch event USB device attached for UserFS daemon. So when connecting a USB drive to iPhone, LaunchD detects an IOKit event that we want to add a removable block storage device to iPhone. It then launches UserFS daemon to handle this event. Once UserFS starts, it registers a callback for IO media matching notification. When XNew kernel finishes creating device file for the USB drive, it will send an IOKit notification. UserFS receives this notification at a new disk named dev. Disk 3 is attached. The callback function attempts to mount this disk by calling an Objective-C method called liveMount and disk. I discovered that the mount disk method is simply a delegate method. It connects to an XPC service called UserFS service and makes an XPC call, create volumes for the device to perform the mount operation. Let's go to the definition of this method in UserFS service. First, it creates a raw device object. Raw means manipulating the device file as a normal binary file. Then it enumerates plugins located under UserFS framework directory and initialize them. Each plugin provides a FSOPS struct, which represents the file system operations it supports. The plugin uses test routine to determine if it understands the on-disk file system format. If this plugin supports this raw device and finds a valid volume with scan volumes routine, it proceeds. If not, moves on to the next plugin. Next step, UserFS service create a mount client to perform the actual volume mounting. The mount volume method is another remote XPC call. Log file provider D provides the implementation of this XPC call. So at this point, control is passed to log file provider D. Following the call stack, I found a familiar command line tool, sbin mount. However, this time the command name is mount LIFS. This tool is a simple mount syscall wrapper. It passes LIFS as a file system type argument for the mount syscall. I believe this is the final step in mounting a USB drive as a UserFS volume. Finally, the EXFAT volume is successfully mounted. The contents of the disk appears at mobile library log files filesystem.userfsd. This is a special directory. All external storage devices will be mounted and here. Now we can access files on this EXFAT formatted USB hard drive. Okay, the process of mounting a UserFS volume can be summarized like this. Compared with the classic mount, it is slightly more complex. Now that we understand how to mount a UserFS volume, let's step further and study how to access file via UserFS. We often write code like this. Use OpenSyscall to get a file descriptor. This is the typical backtrace of an OpenSyscall, where sysopen is dispatched to VNOP open. Under UserFS, the process is similar, except that the OpenSyscall is dispatched to LIFS VNOP open. The following is a pseudocode decompiled from the LIFS kernel extension. Actually, VNOP open is a wrapper for LIFS open request. Let's follow the code and examine its implementation. This function allocates a request for the OpenSyscall. It copies necessary parameters to the request body. It also assigns a unique integer ID to the request, which is an important field that will be discussed later. Next, the function LIFS OpenSend builds a MAC message and sends it to server port. This port is obtained through getLIFS port at the beginning. The message ID is 0x285, which is another important field. After sending the MAC message, this function sleeps and waits for completion of the request. It then extracts return code from the response and returns it to the caller. Now we need to find the handler for this request. Let's switch to the context of process log file provider D. I noticed that live file provider D creates a user client for LFS kernel extension and trying to set a notification port on it. The corresponding kernel code is the LFS set MAC port. This port is the server port mentioned earlier. Therefore, live file provider D serves the actual handler for the open request. Live file provider D starts a make server and waits for incoming requests. Remember this message ID. The make server dispatcher will dispatch the open request to the appropriate handler based on the ID 0x285. The make handler extracts arguments for open syscall from MAC message, then calls the function LIFS open send to resolve the file handle for the FS node. It then calls an Objective-C method li open with mode on FS project. In the reply block, it sends the return code of open request to user client through this method. It is a wrapper for IO connect core struct method. The responding external method for that IO connect core is the method generic reply. The LIFS request done makes the original open syscall caller and tells it the result of Userspace syscall. I mentioned earlier that the LIFS open syscall sleeps on the request and waits for its completion. So now it is woke up and gets the result of opening the target file. It can continue executing and return the result to Userspace code that initiates the open syscall. It seems that I can attempt to summarize the control flow of open syscall under UserFS. It looks like this. A Userspace program initializes access to a file in a UserFS volume using open system call. An LIFS kernel extension takes over the syscall, forwards the open request to Userspace daemon live file provider D. The daemon serves as the actual handler, converting the kernel call to a Userspace call. But wait, there is another problem. I found that the control flow doesn't extend to the file on the UserFS disk, so I must step further. Let's continue with this method. It also acts as a delegate. This method will be dispatched to multiple file provider implementation. In the case of UserFS, the topic of today's talk, the actual implementation is this one, class LFS volume, a method li open with mode. Its code resides in the UVFS service process. So what does it do? Actually, li open is simple. The main work of open syscall is implemented in li lookup. Resolving vnode for file path is actually lookup. So I will only discuss this li lookup method. Remember the FSOPS struct. It is exported by UserFS plugin. The lookup API from UserFS plugin is called. And if the file node we want is successfully resolved, a special UVFS node is returned. A UVFS node is the native representation of a file in UserFS. It is equivalent to the struct vnode in the kernel. Then the Objective-C layer will create a wrapper called LiveFS node. UVFS service replies to the live file provider D using this object. So all questions about how to access files while UserFS are resolved. The plugin exfat does the real job for the file system syscall. I have listed some functions exported by EXFANT plugin. For example, API EXFANT read is responsible for read system syscall. API EXFANT write is responsible for write syscall, and so on. Okay, finally, I get full control flow of open syscall or UserFS syscall. If you want to analyze other UserFS syscall other than open, read, and write for other type of file system like APFS and HFS, you can use this image as a guide. I believe it should be useful. Okay, now that we understand how UserFS works, let's get through some real-world vulnerabilities I found in UserFS subsystem. This is the exploitable kernel bug I mentioned at the beginning. It is caused by a lack of checks on attribute entry offsets. As a result, I can overwrite some data outside attribute data area. For instance, the control field and header of the struct. This is an exploitable vulnerability. It is about extended file attribute. However, EXFANT file system doesn't support this feature. XNew provides a compatible layer. The vulnerable code exists in its compatibility code. The logic is similar in UserFS, but the code is completely rewritten. The corresponding code is shown below. If target file system like EXFANT doesn't support extended attributes, that file will create a compatible layer 2 named Apple Double Manager. So the first vulnerability is UserFS version of the kernel line. The relevant logic is found in method load_attr header of class loudf as Apple Double. The pseudocode shows that the validation of attribute entry offset is also insufficient. So I can overwrite non-data members of Apple Double struct. Now that I know well enough about UserFS, I can conclude that this kernel bug also impacts iOS, but only the UserFS code is affected. The UserFS version vulnerability still exists in versions below iOS 16.2 and was not fixed until I reported it again. I think the root cause of CVE 2022 42861 is the bug fix for UserFS lost synchronization with kernel FS. This is the next vulnerability. It was found while I was studying UserFS. It is another XATTR bug in kernel FS. This is the patch for this bug. We can see an extra check was added against the offset of resource fork entry. Without this check, I can overwrite something like this. This is part of my bug report. The ability of this bug is limited. It can only overwrite a fixed number of bytes beyond a 64 KB kernel heap buffer. For example, I can write 1 byte FF to the header of an object following the 64 KB heap buffer. This seems like useless, but I just happened to read a slide. It is tales from the iOS, macOS kernel trenches. The author is this guy, Jicker. It introduced an amazing key message type confusion primitive, which only requires 1 bit overwrite. With this powerful exploit technique, I can exploit the second kernel FS XATTR bug. The image shows that I was able to get a root share on macOS 12.0.1, but then the primitive was patched in iOS 15.2, making it difficult to exploit this bug on macOS versions higher than 12.1 and 13. Of course, there is a corresponding UserFS version of this bug. The vulnerable code can be found in method load AD header of class livefs ample double. The UserFS logic is the same as kernel FS, lacking checks on entries offset. Therefore, the UserFS is affected by this bug too. Many people may wonder if it's possible to exploit kernel via UserFS. For Userspace OOB bugs, the kernel version of them have been proved to be exploitable. So in theory, they are exploitable, though I haven't tried. For kernel space race condition bug, it can be converted to a kernel UEF. While it is very hard to write a workable exploit for it, it is exploitable in theory, but I didn't try. Because in iOS, the sandbox is always on. App cannot access LIFS kernel extension directly. To solve the problem, we can chain the Userspace, the UserFS OOB bug with the kernel bug and attack kernel indirectly. So I think it is possible to attack kernel via UserFS, at least in theory. Next, let's talk about the changes in file system security model. In traditional kernel FS, a syscall is handled in kernel by a file system extension directly. In new UserFS, LIFS kernel module is very simple. Just forward the syscall to user space daemons. A syscall is actually handled in file system plugin. So the core stack of file system syscall is changed a lot. As a result, the main exploit target tends to user space daemons in UserFS. If a bug is successfully exploited in kernel FS, we could directly obtain kernel read-write privilege. But if a UserFS bug is exploited, we could only take over a sandbox user space process. So UserFS will reduce the impact of FS vulnerability. In addition to the benefits of UserFS, there is also some disadvantages. UserFS is an extra feature. It doesn't replace kernel FS. Kernel FS is still in kernel. The attack surface of FS is now kernel FS plus over user plus UserFS. So the attack surface of FS is actually increased. But on iOS, only APFS and HFS are kept in kernel. EXFAT is forced to be handled by UserFS. Actually, kernel FS and UserFS have almost identical functionality, but Apple needs to maintain two code bases now. It is a challenge that keeps bug fixes in sync between them. And last, as I analyzed above, there is XPC everywhere in UserFS. The core path of UserFS system core is very long. So what about the performance? Actually, compared to CPU USB disk, is too slow. I think the performance is acceptable. Okay, at last, I would say that more modules, more bugs. Introducing new features will also introducing new attack surface attack surfaces. There is a chance to break iOS through UserFS, but when accessing files stored on USB disks, only UserFS takes effect. In this case, UserFS can significantly reduce the impact of file system vulnerabilities. So, overall speaking, I think UserFS is a successful effort by Apple. Okay, thank you for watching. That's all of my talk today. I hope you enjoyed it. If you have questions, you can find me on Twitter. Thank you.